So if this class goes like last class, I probably won't finish the lesson. So I'm hoping that after we grade your guys' quiz tomorrow, we'll be able to have like an extra like maybe 10, 15 minutes to do one more problem like this. But anyway, if not, we'll find time to squeeze it in somewhere. But today what we're looking at is piecewise functions. We're really looking at the first thing we're going to do is I'm going to show you guys a common AP question that's asked when dealing with piecewise functions and limits. The next thing I'm going to do is I'm going to talk to you about how we deal with absolute value functions in calculus, because really what we want to do is we change absolute value functions into piecewise functions, and there's a reason for that, and we'll talk about it there. So that's our two topics. Mainly we're talking about piecewise functions. That was the big picture view. So let's do that. So go ahead and start by writing down example 1, please. So here's what we want to do is I want this piecewise function to be continuous. And it all depends on what I choose for this letter. Okay? Yeah. You know it already? What is it? -1. I think you might be right.
Yeah. Well, I started, well, not only do they both equal 0 at 1 if you make that -1, but also if you just like draw it, you can see that the only that we know the y-intercept's got to be 1 because it's 0. So you see this is 0, this is 1. This goes however you like. It's got to go down, and it's got to go down by exactly 1 in the space element. That's just -1.
Beautiful. That's right. I like that. Good mathing.
That's what I mean by 0, but like I don't know. I don't know. I couldn't piece it together.
I like how you guys are thinking here about these. That's good. That kind of out of the box thinking and just reasoning with numbers is going to be very helpful to you on your AP exam. So what I'm going to do is I'm going to give you guys kind of like a way to approach this based on things that we've learned. And it should pretty much get you through any of these types of questions. And this is the question that you actually see quite frequently on the AP exam. They sometimes make it a little bit more complicated by adding something else called differentiability, which we haven't really talked about too much yet, so we're not going to do that now. But for now, we're just going to focus on what value would k have to be in order to be a function. So I'm going to come at this from Brody's perspective. What kind of a function is that, guys? What do we call that? Yeah, which is a linear function, right? It's just a straight line, correct?
Yeah.
What about this? Quadratics, which are like a U shape. Now, both of these are technically polynomials, and we know that polynomials are continuous everywhere, right? So we know that this line has no holes or gaps. This one has no holes or gaps. So we have a straight line, and then we have a parabola. The question is there a gap between them, or do they connect? Okay, well, we're going to make it be this. We're going to make sure that they actually connect, because we get to pick what k is. So our job is to find what value of k will make those two functions hook up. Okay? So we're playing the role of Cupid today. We're going to make these guys connect. All right. So here's how we do it. In order for those two pieces to connect, the limit from the left would have to be the same thing as the limit from the right, correct? Where they're joining up. So they join at x equals 1. So the limit at the left of 1 and the limit from the right of 1 should result in the same y value. So here's how we're going to do it. The limit as x approaches 1 from the left should be the same thing as I take the limit as I approach 1 from the right. Okay? So that's what will make these two pieces connect, is if the limit from the left and right are the same. Now, if I'm coming at it from the left, what piece do I use?
The top.
So I'm going to replace f of x with kx plus 1. And if I'm coming at it from the right, we would use the other one, right? Now, both of these are continuous functions, right? So how can I find their limits? Direct substitution. So we just plug it right in. So if I plug in -1 here, don't I get negative k plus 1? And if I plug in 1 here, oh wait, not -1, positive. We're plugging in a positive 1. My bad. So if you plug in a positive 1, you get k. Over here, if we plug in 1, we get 1 squared is 1, 2 times 1 is 2, and then 3 just stays the same. Combining all these together, we get 0. And Brody was right. K equals -1. That's the value of k that would allow those two halves to be converging at the same point. Okay? So here's the concept. The limit from the left and right have to be the same, but from there, the algebra will tell us what value of k works to make that happen. Okay? Can I erase? Really? I'm not sure if you're serious or not. Well, okay. Okay. There you go. Clear. All right. So here we go. Let's do this. So what we talked about was, you guys know that the limit from the left has to be the same thing as the limit from the right. But the big question here is the limit from the left. So let's find out. Andy, what is x supposed to be approaching? 7. Remember, it's where those two pieces are connecting, and they're connecting at 7. Or we're going to make them connect at 7. So that's what goes here. So we have left and right. Now, for the left, Christian, what if I'm approaching 7 from the left, what piece do I use? Good. So that's this, right? And then for the other one, we use the other function, right? So it's going to be 1 over 7 x squared plus ax minus 5. Samantha, what do we do now? Direct substitution. So if I do that, we have the following. Okay, so let's simplify this. 7 minus 3 is 4. The square root of 4 is 2. And 2 times -2 is -4. Here we have 7 squared is 49. 49 times the 7th is what?
7.
Combine 7 and 5 together.
2.
Minus the 2. And then divide. The answer is -6 over 7. So Julian, I think you have the right answer. We just did. For some reason you had it reversed. All right. So that's a very common type of AP question. All right. Let's continue our journey here. I don't want you guys to write this slide. I just want you to watch with me for a second. So you guys know that absolute value functions look like a V, right? So this is the graph of y equals the absolute value of x. But let's talk about that a little bit more. Calculus doesn't really like absolute value functions, so we're going to do something about this. Calculus doesn't like sharp turns. The reason calculus doesn't like sharp turns is because there's no slope there. Yes. But also because they have no slope. The reason why is because this one has a slope, doesn't it? This one has a slope, but when they meet, what's the slope? It's not 0 either, because let me show, it's undefined. Here's why. Because I could draw a tangent line that's horizontal, right? That would be 0. But couldn't I also draw a tangent line that does that? There's really no slope at that point. It's just anything goes. So the slope is undefined. Now, slope is pretty important in calculus, isn't it? So that's why we don't like sharp turns in calculus. So what we do then when we're in calculus, a lot of the time when we're dealing with absolute value functions, is we rewrite them. Yeah?
Why does x get to be 0?
That's a
Why does
good
X get to be
question.
0 instead of negative X?
That's a good question.
How dare they?
I know it's a little discriminatory, but we'll talk about why that is. So, well, they're not people, so they're numbers. So we could say it's numberist. But you know what? You kids are like the worst. You guys are so discriminatory against fractions. It's terrible. You guys be hating. You guys be hating on the
I love that.
Good man. Good man. All right. See, you're trying to close the gap. I like that. All right. Anyway. Okay. Anyway, back to our situation here. Where was I? So in calculus, we don't like to think of an absolute value function as a function. What we like to think of an absolute value function is as one line connected to another line. Okay? Because lines work nicely with calculus. These don't. So here's what we do. You guys agree, what happens if I plug in a 3? What do I get? I get a 3. What happens if I plug in a negative 3?
You get negative 3.
You get positive 3. So if you plug in a number that's bigger than 0, yeah, but 0. If you plug in a number bigger than 0, does it change?
No.
But if you plug in a number that's less than 0, does it change?
Yeah, positive.
Okay, so here's the deal. Basically, for any number that's less than 0, it changes whatever's inside, right? So it becomes the opposite sign from what it was. For anything bigger than 0, it doesn't change what was on the inside, correct?
So it's positive no matter what, basically.
Yeah. Yep, that's exactly what absolute value does. So this is how you change a absolute value function into a piecewise function. Notice there's no more bars here. So here's what you do. All you do is you find the breaking point where it splits up, and that's at 0, right? Anything to the left of 0, you change the sign. Anything to the right of 0, you keep it the same, and you just don't need the bars anymore. This is literally the same exact equation as this. It's just written as a piecewise function. So now in calculus, we can deal with those pieces separately and not have to worry about this crazy sharp turn. Now Brody was asking, why does this one get the equal sign, but this one doesn't? In other words, that point exists, doesn't it? So you have to be able to put the dot somewhere. And actually, here's the thing. You could put it on either one. It doesn't matter. I just put it on the bottom, but you could put it on either one. Technically, with piecewise functions, you wouldn't want to put it on both because usually one piece gets it and the other piece doesn't. And that matters with a jump discontinuity. But with absolute values, it really doesn't matter. Anyway, there it is. So we're going to do a pre-calculus thing. I actually taught this last year, and I don't know if Mr. McMillan did, but what we're going to do is we're going to, and he may not have because it's really not that important of a thing. No. You've been doing that all class. You're good. Now.
What? Okay, first of all, don't give me Don't give me that.
All right. Write down this problem here. Here we go. So what we learned is that anytime what's in here is less than 0, the sign changes, right? So that's the first thing that we're going to do, is you're going to take what's on the inside and you're going to make it less than 0. Okay? Now, let's solve for x. So what this means, you guys, is anytime x is less than 3, this function's sign is going to change. The absolute value will change its signs. Okay? For anything greater than 3, it won't change. So now I'm ready to write a piecewise function. You guys ready? Okay? But that makes me want to tease you more. I don't know if that works well.
You guys could be related.
All right.
Manuel, we're not related.
The law changer, like they were dyslexic in this.
Okay, here we go. So we're going to split this absolute value function up into two pieces. For one piece, it's going to be where x is less than 3. And for the other piece, it's going to be where x is greater than or equal to 3. And it doesn't matter which one you make equal to. Okay? Now, what did we say happens for the piece that's less than 3? The sign will change. So check this out. I'm going to write this function all over again, but I'm going to get rid of the absolute value bars. I'm just going to put parentheses instead. And I'm going to put a negative in the front because it changes the sign. So it's going to look like this. Negative 3, parentheses, 2x minus 6 plus 8. So no more bars, and the sign changed because that's what happens when x is less than 3. Now for the one where x is greater than 3, I'm going to rewrite the whole thing, but I'm not going to change the sign. We're still going to get rid of the bars and put parentheses, but we're not going to change the sign. So this one's going to be 3, 2x minus 6 plus 8. Okay? So what I've done now is I've taken the two halves of this absolute value function, I've split it up into two lines. Anything to the left, that's that line. Anything to the right, that's that line. Now technically, this is correct, and you can leave it like this. However, since we're doing this so we can do calculus, which we will later, it's probably good to simplify these. Okay, so I'm going to simplify them. So, distribute, you're going to get negative 6x plus 18 plus 8 is plus 26. Distribute here, you get positive 6x minus 18 plus 8 is negative 10. This equation is exactly the same thing as this equation. The only difference is this one is broken up into the two pieces that calculus likes. This thing puts them together where they join at a sharp turn that calculus doesn't like. Okay? So, step one, let's review. Step one, take what's in here, make it less than 0, and solve. That tells you the place where the function will change its sign. Okay? So then we write it. Step 2. You have less than 3, you have greater than 3. And for the one that was less than 3, we rewrite it with a negative in the front. Or you change the sign. Probably a better way of saying it, because if there was already a negative in the front, that would mean it's a positive, right? Change the sign. Then simplify. Step 3. That's just pre-calculus. There's no calculus there, but we do it so we can do calculus. Okay? So I'm going to throw one at you guys. There you go. So now that we know how to turn a piecewise function in, absolute value into a piecewise, now we can do some calculus with the absolute value, and that's what our next thing is going to be. One question I saw on the AP exam is proving that an absolute value function is continuous. Now we know it is, right? Because we know what absolute value functions look like. They look like a V. You see any holes, gaps, or jumps? No, that's continuous. But you can't say, well, because it's a V shape, there's no holes, gaps, or jumps. We're done. You can't do that. When they ask you to prove that it's continuous, you have to go through that process we learned yesterday. What's the value of the function at that point? What's the limit from the left? What's the limit from the right? Are they all the same? Ding, ding. Okay, so that's how we're going to approach it. So let's go ahead and do one like that. Go ahead and write down example 3, please. I want to determine if this is continuous everywhere. Okay? So the way we're going to do it is, we know calculus doesn't like absolute value, so we're going to change it. Ready? I might buzz through this part a little bit quicker. And in fact, if you don't want to write it all, you don't have to. But that little negative will make that little difference I talked about earlier. So let's see. So first of all, we take the part that's inside. We say, okay, it's less than 0. We're going to add 9. We're going to divide by negative 3. But when you divide by a negative, what happens? So that means now when x is greater than negative 3, not less than, but when x is greater than negative 3, the sign is going to change. Okay? So now when I write my function, it's going to look like this. So this time when x is greater than negative 3, the sign's going to change. So what I'm going to do is I'm going to write negative parentheses negative 3x minus 9 plus 5. And then for the top where it's less than negative 3, it won't change the sign in front of the parentheses. Because when you divide by a negative, when you're doing inequalities, it reverses it. Did you really want me to repeat that, or did you? Okay, so when you're solving an inequality and you divide by a negative, it reverses the arrow. Okay, so that means now that notice I've got the negative outside the parentheses on the bottom instead of the top because of that little switch. All right, I'm going to go ahead and simplify this though. So on the top we have negative 3x, negative 9 and 5 makes negative 4. On the bottom I'm going to distribute a negative, so that's going to be a positive 3x and a positive 9, which when you combine it with 5 makes 14. Now that's not the answer, so but I'm going to box it just so I know that we're not using this anymore. Now we're using this. So now we can do our calculus. So I want to prove that this is continuous. So what's the first thing that we have to do if I want to prove this continuous?
Check f of x.
Find f of x. What? Now, first of all, is this continuous everywhere?
Yes.
Yeah, those are both just linear functions. So we know there's no holes or gaps or jumps anywhere on those pieces. My only concern would be, are they joining up at the same spot? Now we know they will in this case, but let's go ahead and verify it. So I need to check to see if it's continuous at negative 3, right? So what piece am I going to use for that? Negative 9 and 14, 5. Okay, now what do? We've proven the function exists there. Prove the limit exists. So I want to find the limit as x approaches what number? From the left. Now if I'm doing it from the left, which piece do I use? The top. And that would, since this is continuous, I could just do direct substitution, correct? So let's do that. Negative 3 times negative 3 minus 4 is 5. Looking good so far. Limit from the right. I'm going to use the bottom piece for this, which is 3 times negative 3 is negative 9, plus 14 is 5. They're all the same, right? That's good. That means it's continuous. That's what we learned yesterday. Was anybody not here yesterday? You were here yesterday. Physically. I don't know about mentally. But I saw your person here yesterday. All right. I know a picture. What do you do with some pictures? All right. So now, guys, how you write your answer matters. Okay. What do I write? I write yes because what? Okay, the limit of f of x. F of what? There you go. This is your answer. That's my answer. That's my explanation. So I'm going to give you guys one, and yours is actually an absolute value function, but it's not a normal absolute value function. So yours is actually going to turn out to be not continuous. And your job is going to be to, first of all, turn it into a piecewise function, right? But then I want you guys to go through your steps here to figure out why is it not continuous? There's a problem, okay? And then see if you can write down the answer in the correct way. Muy bueno? All right. Grace? There you go. So step 1, changing into a piecewise function. Step 2, do your 3-step process to see if it's continuous and explain why it is or is not. something that's not continuous, okay? So here we go. First of all, you guys should have started off like this, right? Then we do our piecewise function. Okay? Now, if you left it like this, you're still going to catch the problem, okay? Because the first thing you need to do is you need to find out what is f of 1. And since I put the equal sign down here in the bottom, I'm going to use that one. And I get this, which is undefined. So right there, you could stop and say, no, this function is not continuous because it's not defined. But remember, I told you guys that does this equal have to go on the bottom? It could have went on the top, but would that matter? You'd still get undefined. So this is technically not written right, just so you guys know. Am I allowed to plug 1 in? No. So should I have an equal sign anywhere? I should not. It's not possible to plug in 1, so you shouldn't have an equal sign. Now, I don't expect you guys to have done that on your own, but now I'm telling you, so now you know that it's possible that when you split it up, one of them lose their equal signs, right? That's possible. Not always, but it's possible. Now, some of you guys went the extra stretch, though. Some of you guys might not have gotten that, because some of you guys realize what's x minus 1 over x minus 1. Some of you guys just simplified it to 1, which is good. That's actually good. Now, but that might lead to an error, because you might think now, by writing that, you might think, what is f of 1? You might think you might have thought it was 1 and thought, okay, we're good. That's not necessarily true. Because remember how I told you it could have been up here? In that case, it would be -1. So which is it? You don't really know. So you might have missed that, okay? But that's okay, because you still would have caught it as not being continuous. Here's why you would have caught it. Because even though you would have gotten tricked here, as you took the limit from the left, you would have found that it's not the same thing as the limit from the right. Because as you approach 1 from the left, it's -1. And as you approach from the right, it's +1. They're not equal. So you could have also said no, because the limit from the left and right are not the same. Okay? So that would have been fine. That would have been fine. Yeah.
So, do we get points off?
That's a good
reasoning?
question.
Like,
So check this out. I was just thinking that. I'm glad you asked. Would you lose points if you wrote this? Let's say you said no, because, right? And then you wrote this. I think, I'm not 100% sure, I think they would give you full credit. Because you can have something incorrect written on your paper, but it doesn't really affect the process, so I don't see why they would care. But I could be wrong. But they have no, because what they do is they come up with, if I see this, they get a point. If I see this, they get a point. They don't really have, but if I see this, they lose a point. They don't do that. So I'm pretty sure they wouldn't do that.
Well, I don't even write down one. It was 1. As soon as I simplified it to 1, I saw that a little bit now listed.
And that's even better, right?
So I just put no because
Yeah, yeah. Great. So that's that. We have more, but we're going to save it for tomorrow. But tonight is your quiz, right? Tomorrow we're going to grade that quiz in class together. And then we'll try to finish the lesson up tomorrow, hopefully, if we can. There's just one more problem I want to go over. So that'll do it, dudes.